Hello and welcome to a video on calculus. So today we are going to talk about calculus. In the 17th century, Gottfried Leibniz and Sir Isaac Newton discovered a study of mathematics known as calculus. And calculus, let's write this down here, occupies a very big place in mathematics. Now calculus seems to be a pretty weird name, but let me tell you what this means. Calculus deals with the instantaneous rate of change of a quantity with respect to the other. And the reason I wrote this over here is because this is the core of calculus. And so one of the things that you may have in your mind is, what does this mean? And we'll look at this. But before that, let me tell you what calculus comprises of. Calculus comprises of two subparts known as differentiation. Write this down. Differentiation and integration. All right. So now let's see what this term means. So now imagine that you are driving a car. Now, due to some reason, the speedometer stopped working. Now, provided you have the odometer, that is the device which measures the distance, and you have a watch, that is you're given the time. Can you find the instantaneous speed? Let me write this down here. Given distance and given speed, given time, can we find the speed? Now we can obviously find the average speed, right? That is the speed between 2 points. Between A and B it is 12 meters and the time taken to cover is 6 seconds. The speed is 2 meters per second. This is average speed. But can we find the instantaneous speed? Now what is instantaneous speed? Instantaneous speed is the reading of the speedometer. Like suppose if you have seen the speedometer, it gives the speed at every single second, right? Okay, now let me give you another challenge. Let's say that you have given speed, okay? That is, the speedometer is perfectly working, but the odometer stopped working. So you don't have the distance, but you are given time. That is, you are given the watch. Can you find the distance? And so in the first case, solving this part of the question is dealt by in differentiation, and solving the second part of the question is dealt by integration. Okay, and now in this video we'll particularly discuss about differentiation. All right, so before discussing about differentiation, let us define what is a slope. Now the literal meaning of a slope is actually a slanting line, right? Yeah, that is something which we know what a slope is. But in mathematics, slope is defined as the tan theta, provided that this is theta, or it is given as the perpendicular distance divided by the adjacent distance, okay, which is nothing but tan theta. Or if say that this was on a Cartesian coordinate system, or if it was on a Cartesian plane, okay, then in that case it would have become the change in the y coordinate, which is delta y, and the change in the x coordinate, which is delta x. And delta is something which we use to denote change. Okay, so let's say that this is point x1 comma y1, and this is point x2 comma y2. So slope in this particular case is going to be the change in y, which is nothing but y2 minus y1, That is this particular distance, yeah, this particular distance divided by the change in the x coordinate, which is this particular distance, which is x2 minus x1, is called the slope of this particular line. Okay, now let's move forward. So we know what a slope is, right? But now, if I ask you that you're given a system of Cartesian coordinate, yeah, and let's say that you don't have a straight line, and I ask you to find the slope of this curve. Now, what can the slope of this curve be? Now, the way in that particular time, mid 17th century, Gottfried Leibniz thought was that I know how I can find the slope of a straight line, but a curve, yeah, a curve can be imagined as made up of very small lines, right? Infinitely decimally small lines. Let's select this. We have small lines, which actually at the end of the day makes a curve. So suppose we have to find a curve at this particular point A. Now the curve at this particular, the slope at this particular point A can be defined as the slope of this particular line, which is nothing but the slope of the tangent at point A. Let me write this. At any curve, slope of a point is defined as slope of tangent. And you can clearly see why this is true. And so at this particular point, the slope would be this distance, which is delta y, and this distance, which is delta x, or particularly tan theta is going to be the slope. Okay, now let's say that I don't give you this angle. Okay, now how are you going to find it? Yeah, and if you don't have any of these things, so in this case, how will you find it? Let's take a look. And so let's bring back our Cartesian coordinates. And in this case, this is going to be our x-axis, this is the negative of x, y, and the complement of y. All right. Now let's say that this is our curve, I'm sorry. And let's say that this is a point A and this is a point B. And so slope at the particular point B is actually slope of this tangent, right? Now I'm going to make a claim. The slope of this tangent is the slope of this secant. That is, slope of AB is equal to slope at B. Now, once I say this statement, I know you're going to shoot me in the head, right? Because, of course, this seems to be the most absurd thing in the world. How can the slope of this line be the slope of this line? I'll tell you. Let's say that you slide this point A down. So first it's here, and then you slide, let's say that you have slide the point down about here. So this is that AB. You slide it here. This is the AB. And when you get this infinitely decimally small, right? When you get A to this particular point, then in that case, it is going to be the slope at B, because at that point, AB will coincide with tangent at B. That is, what is the slope at AB? The slope at AB is again delta y by delta x. And so basically what we are doing is we are taking the delta x very close to 0. We are not taking it at 0. We are taking it to be very close to 0, right? So here delta x, as delta x tends to 0, our secant AB is going to coincide at the tangent at point B. Right, so this is something that we have to do. Now, if you don't know this, it's okay, you'll learn it further. But to solve this particular kind of questions where delta x tends to 0, we have to take the limit. Okay, and let's say that point B here, the point B here is x comma y, and let's say that this is x2 comma y2. Let's keep this x1 comma y1. Okay, now we're going to solve this using limits. So this can be written as limit as delta x tends to 0 of the quantity delta y by delta x, right? Because this is tending to 0, right? And only in that particular case we can coincide the secant AB to the point B. Okay, so limit as delta x tends to 0 of the quantity delta y by delta x is equal to y2 minus y1 divided by x2 minus x1. And so when you solve this thing using the limits, you get a value or you get a number, right? Let's say that the number is 2. Okay. And so this 2 is actually the slope at point B. All right. I hope you're getting this. Now let's look back here. Let's say that we calculate the slope at point B and we have it as 2. So let's say this is 1, this is 2, this is 3, this is 4, so on. So at point 3, the slope is 2. Let's say at point 2, we have C, and let's say the slope is 1. And so what we do is, once we take the slope at every single point, let me write this down here. Once we take the slope at every point on the curve, so we get a table, okay? And let's say that this is the slope and this is the x value. So let's say that at x equal to 2, the slope is 3, and we have some particular values. Okay, we have some values. If you know, it's called the truth table. Yeah, and so at that particular point we have some values. Now what we do is, let's say that we again plot these points on a Cartesian coordinate system. Yeah, so at x equal to 2, let's say that this is y is equal to slope. Y is equal to the slope. This is the x. So at 2, y is equal to 3, and so on. We plot some particular sets of points, and at that particular points we have a straight line. Yeah, or not necessarily that we get a straight line, we get some particular figure. Yeah, some particular curve, anything. And so in this particular case, this line is what we have got. Okay, which, okay, now one of the things that you might be thinking wrong is that as delta x tends to 0, delta y also tends to 0, right? Delta x is tending to 0, delta y is tending to 0. Then shouldn't delta y by delta x both tend to 0 and be of the form 0 by 0? Yeah? But let me give an example. It is tending to 0, it's not 0, okay? So, as delta y tends to 0, as delta x tends to 0, it is a number which is very, very close to 0. Let's say that this is 0.0012, and this is like 0.0008, or let's say that it's 4. Okay, and so we get on dividing this, yeah, as delta y by delta x, both of these tend to 0, but we get a solid number which is 3. Yeah, so this is something which you don't have to get confused. All right, so now you might be confused as to where we are going, so let's revise what we have done till now. Let's see that. Okay, so in the first case we had a Cartesian coordinate system. And in the second case as well, we had a Cartesian coordinate system. And so what we did first is we had a slope, yeah. Then we calculated tangent at every point, or we calculated slope of tangent at every point. And with its x values, from this we got this graph, yeah. And this particular graph is said to be the derivative of this particular graph. Yeah, amazing, right? And so let me give you a real life application. And let's take a look at our problem where we had the speedometer which was not working and we had the odometer and time. Okay, so let's again have our axes, and let's say that this is the distance, yeah, and this is the time. So we have the ST graph. All right, and we have a curve which demonstrates the journey. All right, and so what particularly happens is when we take the derivative of this particular ST graph, or we take the derivative of this particular curve, yeah. Once we take the derivative, let me write this down. This is a very, very important word. We get some particular graph, yeah. Let's say it comes to be this straight line. And so the derivative of the distance time graph gives us the velocity. Sorry, I'm sorry. This it gives us the speed time graph. Yeah. Let's denote speed by v. Okay. And so once we have the speed time graph, you might just notice that at, let's say that at 3 seconds we had the velocity say at 5. At 6 seconds, let's say we had the velocity as 7. And so in this particular case, we have instantaneous speed, right? Because at every single point in time, we have every single point of velocity. Yeah, in this particular case, we have distance. With time, we have distance, right? But in this case, with time, we have the speed, and hence, on calculating the derivative, we have the instantaneous speed. And so this notation is given by dy by dx. Now, again, don't be scared of this. This seems to look horribly confusing, but it's okay. It's just a notation. And so dy by dx is actually denoted as the derivative of, so write this, derivative of y with respect to x. Okay, and so this is what derivative means. Now, so what we did in our example was that we calculated the derivative of the speed time graph with respect to time. Yeah, and we got, what did we get? We got a velocity time graph, which, oh sorry, I'm sorry, we got the speed time graph, which gave us the instantaneous speed. And so what we did again, let's revise what we did till now. First, we calculated the slope. We defined the slope. Then we had a curve. We took the tangent of that curve at every single point. We plotted it out on the graph. We solved its limit. Yeah. And so now what we did was that we took the curve. Then to calculate the slope of the tangent at every single point in the curve, we calculated the limit. Because remember, in this case, when AB tends to 0 or delta x tends to 0, at that particular point, it will come to the tangent at point B. And so we calculated it using limits. And after that, what did we get? We got the slope. Yeah, we got this particular slope. And then we plotted the slope on another graph. And we found that this graph is said to be the derivative of this graph. Yeah. Now, The derivative of some other common functions is given as follows. The derivative of, or say, how to calculate the derivative is given as follows. Ladies and gentlemen, thank you for sticking with me till the end. I hope you understood differentiation today. I will upload the video of integration in the possible next week. So thank you for watching. This is Sci-Fi Thinker signing out. Science.